On the border between Westmoreland County and Fayette County lies the 33.4-mile-long tributary of the Youghiogheny River known as Jacobs Creek. Jacobs Creek is traversed by the Pennsylvania Turnpike 4 miles west of the Donegal exit. The turnpike runs directly over the former site of the Mount Pleasant blast furnace, which sat on the southeast bank of Jacobs Creek. The furnace's operator, William Freeman, would eventually have the waterfall upstream from the site named after him. A foundry and the remnants of a large water wheel still occupy the right upstream bank. Another indicator of the area's past is the large stone, concrete, and steel dam approximately 400 feet downstream from the falls. That dam, often referred to as the Freeman Falls Dam, was used to flood the area for residents to swim. At approximately 80 years old, the dilapidated dam has become a source of concern for its owners, who contacted American Rivers to inquire about its removal. We are here today to present the removal plan we created for American Rivers. Hello, I'm Mike Schmizzi, and with me today I have the other members of Castor Construction. Luke Holbert, Lizzie Kellenbeck, Kira Klein, Andre Shefflin, and Kara Schmidt. At this time, we also wanted to take a moment to acknowledge Lisa from American Rivers and thank her for all of her help on this project. We're going to present to you our plan for the removal of Jacobs Creek Dam near Freeman Falls. We will start off with a brief description of the project and why it is necessary. Then the members of our water resources team will discuss the site as well as how we ascertain the data for our hydraulic and hydrologic modeling. Modeling the dam site both before and after removal will be discussed before our construction management team explains the testing that was performed at the site. We will then show the necessary work done for permitting before discussing various removal options and giving our recommendation for the best removal process and reasoning behind it. So the scope of the project in the broadest sense is the removal of a privately owned low-head dam for American Rivers due to the hazards that it presents. To do this, we must determine how the creek will be altered after removal, obtain permits for the removal, propose alternative plans for the removal, and consider what restoration is necessary after removal. The dam is located on the edge of Westmoreland County near Acme, PA. This map shows the dam's location in comparison to Pittsburgh. We don't have an exact date that the dam was constructed and cannot find any historical information, but we were told that it's been there since the 1940s. The dam is constructed of 3 parts. The center is a large steel plate supported by vertical and diagonal beams. At one point, a pulley system allowed for the raising and lowering of the steel plate to increase or decrease the flow of water downstream. Parts of the pulley system are still visible on the vertical beams, but the system is inoperable. To the left and right of the steel plates are 2 stone dams with concrete tops. Both the left and right side of the dam are severely undercut, and concrete slabs are now cantilevered over the downstream side of the dam. You can see in this photo that the vertical beams are starting to lean downstream from the water pressure being exerted on the center section. Also, the blue line in the photo indicates a large crack forming in the top of the slab on the opposite bank. The other pad has similar cracking. The biggest reason for the removal of the dam is it presents a hazard to the area. The access trail side, or the left side if you're looking at the dam from downstream, is severely undercut its entire length. The rocks that were once supporting the top pad are now laying at the base of the dam or have slid to the bottom of the bedrock channel, which we will discuss shortly. Additionally, that side of the dam is leaking in several places. Our concern is that either the force of the water behind the dam or someone walking on the concrete pad will cause the top half of the dam to collapse. This scenario presents 3 possible hazards. The first one is obvious. Someone walking on top of the dam when it breaks will fall. The second is the potential for someone upstream from the dam to get swept downstream and trapped behind the remaining base of the dam. Finally, the channel downstream from the dam is a large sheet of very smooth bedrock. Debris from a dam collapse will move downstream at a rapid pace and present a hazard for anyone in its path. Obviously, all 3 of these scenarios have the potential for serious injury or even possibly death. Activities that attract individuals to the site include fishing and kayaking. On our last visit, we encountered people fishing both up and downstream from the dam. Individuals downstream are wearing waders and standing in the water. It should be noted that the creek is stocked approximately 2,000 feet to the southeast, making this a popular fishing destination. The area is also frequented by kayakers. Just upstream from the falls starts a 5.7-mile run of Class 3 and 4 rapids that discharge at the bottom of the mountain near the Laurelville Mennonite Retreat. The photo on this slide is someone kayaking over Freeman Falls that we found while researching the site. The falls represent the largest drop on this branch of the creek. Therefore, it is not uncommon for kayakers to start above the falls and then portage around the dam, leading to increased risk of injury. It should also be noted that the conditions at this site are also relevant during the removal process and have been considered in the safety plan. So just as a reminder, we're working in Donegal, PA, which is on the very edge of Westmoreland County. We added an overhead image of the property to show the proximity to the PA Turnpike. The dam is actually visible from the eastbound lane of the Turnpike around 4 miles before the Donegal exit. Now we have Kara to talk about the site visualization work we did for the project.
So I'll be reviewing our site visit that we went to the dam site on February 3rd, 2024 with our mentor, Lisa. During this visit, we did some surveying. We'd like to thank John Senkner from Senkner Engineering for showing us the ropes and helping us use our surveying skills to get some measurements of the area. So we used both this total station to survey as well as a few measurements from the measuring reel, which you can see in the left photo. Some limitations from surveying were that we could not actually go into the water. It was too cold and that would have been dangerous. And visibility was a bit low because the area is so steep and because there's so much thick brush, we could only get 4 surveyed cross sections. However, some pros from the day where we did get all of the data that we needed, we didn't have any gaps. We were very safe. No one fell in the water. No injuries occurred. Nothing bad happened. And we got a set of point data from this. So we used a survey notebook to record it. You can see in this photo, the yellow lines show the cross sections that we were able to survey across the dam, and these were in majorly important survey areas. So we're pretty happy with the data that we got. We then used this data to inform our site visualization. So all of these measurements from both the surveys and the physical measuring tape measurements were used to expand into a set of 27 cross sections in an Excel sheet. We also used some measurements from LiDAR and from Google Maps to help inform this to make sure that our measurements were well-rounded and well-documented. These were imported into Revit to create a visualization tool for this section of the stream. This is really important for 2 reasons. One is that the model can produce a visualization from any angle, any photo, because the visibility and the terrain are so difficult to manage here in person. And it can also specifically produce cross sections and a long profile used in the design drawings. So this next slide shows the important cross sections that we took from the Revit. So we did a different cross section for each major flow regime and stream flow change. It is notable that it was modeled to be a straight stream. In reality, the stream curves slightly, but this is all right because this is just a simplification and the true curve is still shown in our site drawings and on our GIS products. So this is just an example of some of the cross sections we could get from the Revit. The cross section around the dam, the cross section around the island is in the lower left, and it produces these very nice final products, such as this, for example. You can see on the top and the bottom the long sections of the stream, as well as the access path down from that upper driveway. You can see how steep the hills are, get an idea of that. Next, I'll get into the hydrology and hydraulic slides. So just to recap, there are what we're calling 4 flow regimes in the stream section. Flow regime is a hydrology term used to characterize a specific and relatively uniform span of flow in a stream. So like this entire area upstream, we're calling flow regime 1. It's all pretty similar to one another. So I will go through each of these sections to give you an idea of what the stream really looks like. For flow regime 1, it's upstream of the waterfall, so none of our construction will affect this area at all. And it's pretty shallow, relatively rapid flow, but pretty shallow, a few riffles and rocks. Then we encounter the waterfall. It's about an 8-foot drop down to the water surface. So this could be a source of danger if people are not careful. Thankfully, we were all safe on our site visit. The dam is only about 200 feet downstream from this waterfall. So we want to be clear, but by removing the dam, effectively will only lengthen the stream about that far for fish like trout. Next is the pool as a result of the dam, where the water reaches. The water's rather stagnant in this area. We couldn't safely get into the pool to survey, so we want to be clear that we weren't able to get exact water depth measurements here, but we knew several people who were more familiar with the stream that estimated it was around 4 to 8 feet, depending on where you were. Notably, the pool has this sediment island in the middle, which is both earth, like there are actual trees and plants growing out of it, and also presumably a large amount of sediment that has drawn up over time and been pushed against the dam, which is potentially another force that could cause it to fail suddenly, which is why this is important that we're removing it safely and carefully. Next is the actual dam itself. So you can see on the right what it looks like in normal dry weather flow, but on the left is what it looks like in heavy rainfall. So it's completely overtopped in that photo. Another potential safety issue, good to remove it. Next is just the sheet of the dam to show some measurements. So it's only about 46 feet across, but very important for that area. It completely dams up the water. The water isn't going around it during dry flow very much, but it is going over that middle section, which leads into flow regime 3. So this is a pretty channelized bedrock section. So it's pretty smooth. There's not a lot of turbulence. And then it opens up into flow regime 4, where you can very clearly in this blue polygon see the transition of the water, where flow regime 4 is where it opens up into a much more wide open natural channel where it then flows under the turnpike. And this is just a very nice shot showing the dam, flow regime 3, and the pool behind the dam. We'd like to thank Sean Blair Photography for allowing us to use their drone to take some really great photos of our dam. Next, I'm going to give it to Kara to get into the hydrologic modeling.
Now we're going to dive into the more technical side of water resources as I go over the hydrological and hydraulic models that we created in order to characterize what effect removing the dam will have on the stream and surrounding area. To do this, we created two models. We created a hydrologic model using HUC HMS to determine the stream flow at the dam site due to storms such as the 100-year storm, which have certain statistical recurrence intervals. This type of model is created using the watershed's characteristics, which, just to make clear, a watershed is the area that drains to a certain location. And so the watershed for our project is shown in the map on the right. Once we had these discharge values, we then created a hydraulic model using HEC-RAS to determine flow characteristics such as velocity or depth immediately upstream and downstream of the dam locations. The main purpose of this modeling is to see how the stream will change if the dam is removed. Now, to get into more detail on the HUC HMS model, we use this to determine the volumetric discharge at the site as a result of a 100-year storm lasting 24 hours. This is a standard design storm used widely in industry. We first needed the 100-year rainfall, which we found using a resource from NOAA, the National Oceanic and Atmospheric Administration, and we found this to be about 5 inches. From there, we defined various parameters based on characteristics of the watershed in order to determine how much of that water is lost due to infiltration and how quickly water travels across the watershed. The Clark hydrograph is a standard routing method, and we did not use a base flow method since the amount of base flow is insignificant compared to total flow. We use the green and amped loss method since this method is based on soil characteristics such as conductivity and porosity, and so this constrains the parameter values to what is typical for that soil type more than other methods which are more empirical and simpler. This is important because this stream is ungauged, so we knew that we would have difficulty calibrating and validating our model. However, we did initially attempt to calibrate our model using a synthetic hydrograph created from Youghiogheny stream gauge data. As Mike mentioned earlier, Jacobs Creek is a tributary of the Youghiogheny River, which has stream gauges both upstream and downstream of where Jacobs Creek intersects with it. Part of the difference in flow between the peak waves between these two stations could be attributed to water from Jacobs Creek watershed. So we scaled that difference in flow by what percentage of that watershed is the dam's watershed. However, when we use that data in the HMS model to calibrate the parameters, in order to match the HMS curve with the synthetic hydrograph, we had to change their values so much that they did not make sense for the soil type of the watershed. We decided that this probably meant that the calibration data was not accurate, which is realistic because Jacobs Creek is a very small part of the Youghioghany's watershed, and also the closest rain gauges are still a ways away. And so with that, we decided to use our initial values for the parameters, which were based on standard values for the soil type. For some validation, we consulted the United States Geological Survey StreamStats resource, which uses regression equations to calculate the magnitude of certain return period flows. Since the StreamStat values align very well with our results, This gave us an extra degree of confidence in our model. So once we had that peak flow, we started creating our HEC-RAS model in order to determine how that flow would change once the dam is removed. We created what is called a 1D steady flow model, which means that the flow is basically traveling in one direction and the flow quantity does not change throughout the simulation. We ran it with the dam and without the dam under two different flow conditions. The flow that we measured during our site visit, which we are considering the spring dry weather flow, and then with the 100-year storm from the AGCHMS model. This model extends from immediately upstream of the waterfall to about 200 feet downstream of the dam and was created with the cross sections developed for the Revit model. We then georeferenced these cross sections onto terrain LiDAR data using RASMapper, which added more geospatial capabilities and better visualization of the results. And so looking at the results, first we're looking at the depth of the water under the spring dry weather conditions and how that changes once the dam is removed. As we suspected, once the dam is removed, the reservoir behind the dam will drain and the water level in that area will become lower, but increase in velocity. We can see that immediately post-construction, the sediment island in the middle becomes more exposed. And now we're looking at the results of the 100-year flood. We can see that due to the very steep channel slopes, there's not much change in the total inundation area. The main differences are that with the dam, it's just about 2 feet deeper and the downstream channel is slightly narrower than without the dam. The water is also faster and causes more shear stress on the channel bed without the dam. So these models help determine what the immediate effects of the dam removal is, but with the increased velocity and shear, it's extremely likely that the sediment island in the middle of the stream will be swept downstream and slowly erode with high flow events. And so this is not what the final channel will look and behave like in the long term. Also, if the dam were to fail during a high flow event like this 100-year storm, a large wave of water carrying sediment would be swept downstream, which could be dangerous. And then I also wanted to acknowledge the limitations that this model had. As we talked about earlier, we were not able to get into the stream to survey the channel bottom. So we made our best estimations, but there's obviously a lot of uncertainty there. Also, the modeling does not fully capture the sediment transportation that will occur once the dam is removed. We realized that exists additional software that could model this, but decided that this was outside of the scope of the project. And so after all of that modeling and analysis, we determined that there's an extremely low chance of flooding downstream once the dam is removed. As we saw with the HEC-RAS model, this steep ravine slopes really constrains the flow. And so looking at the existing FEMA flood map that we see to the right, we see that similar to the HEC-RAS figures, the floodplain does not extend much outside of the stream's banks. Also, we can see from the figure on the left that there are no buildings downstream of the site near enough to be in danger of potential floods. And so with these figures, we were able to infer that flooding would not be an issue at this site even before the modeling was performed. This kind of modeling is not typically performed for these kinds of low-risk dam removals, but we decided to undertake it anyways to double-check that assumption and to get the full picture of the flow changes. And so now I'll pass it on to Lizzie, who will explain what the changes in flow will do to the habitat of aquatic life in the stream.
To get into the ecology and habitats, we're going to start by characterizing what different features make up a stream or creek. So commonly you will have pools, riffles, and runs. Pools are often areas of reduced velocity, little turbulence, and often deeper areas of water. Riffles are areas of more shallow water levels. They are often submerged obstructions such as rocks, and there is often surface turbulence. Runs tend to fall in between the pools and riffles where there are moderate depths and little to no surface turbulence. So looking at our stream, we can see that there are currently a few different, all three different stream habitats are present within our creek area. So starting by the bridge and before the waterfall, the water is definitely more shallow and there are rocks obstructing the surface. And then we head to the waterfall where again, the stream up until the point of the waterfall is more riffle-like in characteristics. Below the waterfall by the dam and above the dam and by the island, the water is a combination of runs and a pool right before the dam. The water is much more calmer. It is much deeper. And then after the dam, we see that the water is shallower than it was above the dam. However, because of the bedrock, there is still not as much surface turbulence as there was by the waterfall. So it's most likely categorized as a run. So looking at how the stream will look like after dam removal, by using the HEC-RAS modeling, we can estimate that the area before the dam, before the island where the waterfall will stay roughly the same because the waterfall is its own natural barrier. But the removal of the dam will most likely create, at least initially, the island immediately before the dam and near the island to become have higher stream velocities as well as lower water. So it'll be more riffle-like in characteristic. And again, after the current area of the dam, the stream will be still more like a run because of the bedrock that is there. So looking at the ecology that we have in the area, unfortunately, due to the timing of our project, we were not able to do a full ecology survey like we would have liked to, but based on past records of what fish species are common in different areas of Jacobs Creek, we can estimate what might be present in the stream during the time of removal. So we have mottled sculpin, rainbow darter, eastern black-nosed dace, margined madtome, and central stone roller. You can see that all of these species are species of least concern. They're not endangered, and they all also enjoy riffles as a habitat. The central stone roller also enjoy pools, but riffles are acceptable to them as well. So based on our HEC-RAS modeling, we can determine that while the removal of the dam will have an impact on the habitats in the stream, most likely it will just increase the amount of riffles in that portion of the creek, which is overall better for the species of fish that might be present. However, as we did mention previously, the removal of the dam will only affect about 200 feet of the creek downstream of the waterfall because the waterfall, as we said, is its own natural barrier. So even though it is likely to have a positive impact on the habitats in the area, it still won't have that large of an impact regardless. So now I'm going to hand it off to Mike to get into some of the sampling and testing we were able to complete.
Macro sampling was completed to gain better insight to the water quality at the site. Due to the high water behind the dam, we were only able to sample downstream, so we selected 3 areas we assumed would yield very different results. The procedure for collecting macroinvertebrate was straightforward. One person held a kick net a few feet downstream from a second person who kicked up as much debris in the creek bed as they could. The upstream person also lifts rocks up and wipes them with their hand while they are still underwater. From there, the net is taken to the bank and opened up. The macroinvertebrate are pulled from the debris in the net and counted. We gathered a relatively large number of Rhyocophlaidae, the green macroinvertebrate in the center of the slide, and Corydalidae, the centipede-looking macroinvertebrate at the bottom. This is relevant because both of these are very sensitive to water quality. There were also a large number of the orange Phyllopodumdae collected, which prefer a sandy or sediment-filled environment. The amount collected, combined with the fact that the dam is leaking in multiple locations, suggests that the sediment is not building up behind it.
So it is because of the macro sampling that we had gone ahead and decided to do some water quality testing. I had spoken to Dr. Sanchez about where along the stream might it be the most important for us to do some testing. So we had decided that test site 1, which was directly at the waterfall, test site 2, which is directly before the dam, and test site 3, which is directly after them, as you can see by the picture provided. These test sites were just to ensure that we were getting the best readings possible for the stream. And on the next slide, you can see the water quality lab results. From this, I would like to point out 4 of the possible chemicals, lead and nitrogen being the most important, as those affect the wildlife in the stream and native to the stream. And then calcium and magnesium are both very high numbers. I just didn't want anybody to run over this and raise any type of cause to this, as this is consistent with any of the streams in the area. And one of the main things that we're pulling from these water quality lab results is to make sure that the stream can maintain these numbers throughout the construction process, being pre and post. So it is in our hope and in our bid that at the end of the process, of the construction process, that we will have the consistency of these numbers. And now I will pass it off to Andre to go over some of the soil testing that he has done.
So next, we took a look at the quality of the soil on site. To do this, we referenced 2 databases, the first being the California Soil Resource Database, which we used to gather some general information about the types of soil and the subsurface present in the Southwest Pennsylvania region. This gave us some generalizations about what type of soil was in the area and what the subsurface conditions could look like and things of that nature. We then used the USGS soil survey to determine more specific information regarding the conditions of our site. Because we couldn't be sure that the databases were 100% true to our conditions on site, we decided to test the soil ourselves and either confirm or reject the information presented within these databases. So to do this, we collected a sample of soil along the bank of the creek and ran some basic soil property tests like a sieve analysis as well as an Atterberg limit test. Once we ran these tests, we took the results and compared them to the information in the databases to determine if we could confidently use that data. From there, we took some of the tested data and used existing correlations to find other properties such as porosity. So after referring to both the databases and supplementing them with the lab results and correlations, we were able to find that this soil is part of the Craigsville-Buchanan complex, which is a well-draining soil and classified as a well-graded sand. One of the main things we were able to determine from the testing, as well as the given data, was that the surrounding soil would not be susceptible to erosion once the dam was removed. We figured this given that the majority of the subsurface consists of bedrock and the slopes of the bank are not very that steep. Now I'll hand it off to Lizzie to talk about permitting.
One of the main parts we had to do for our project was the permitting. So to start, as we mentioned previously, our dam project is located in Mount Pleasant Township within Westmoreland County within the Commonwealth of Pennsylvania, which are all authorities that we have to keep in mind when coming up with the project, with the removal of the dam. So to streamline the actual dam permitting process, we are going to be using a restoration waiver binder, which is allowed through the Pennsylvania Department of Environmental Protection. This includes a PADEP general information form, which just provides general details and information about the creek and dam area. The Chapter 105 environmental assessment form, which provides more specific details about the dam itself. It will also include a cultural resource notice, as well as a Pennsylvania Natural Diversity Inventory Search, a erosion and sediment control report, and as well as our site plan for the project. So in addition, we also have letters of intent that we will be sending out to multiple authorities. This includes both the Westmoreland County as well as the Mount Pleasant Township Municipal Authority, who are both municipal authorities of the area that our dam falls into. We will also, as a part of the cultural resource notice, be sending letters of intent to the Pennsylvania Historical and Museum Commission, and we will also be sending letters to state and federal fish and wildlife agencies, including the Pennsylvania Game Commission, the Pennsylvania Fish and Boat Commission, the U.S. Fish and Wildlife Service, and the Pennsylvania Department of Conservation and Natural Resources. These letters serve not only to inform the recipients that we are planning on removing the dam, but it also gives them ample time to review our project and contact us if they have any issues with our plans. Here are some templates of the letters that we plan on sending, and now I will hand it off to Mike as we head into our actual plan for dam removal and alternatives.
The first alternative considered was the do nothing alternative. If the dam is not removed, it will fail at some point, most likely soon. And in the event of a collapse, American Rivers is dedicated to the cleanup at the site. A collapse will send debris downstream to multiple locations. Several of the locations are difficult to access. Additionally, the dam is most likely to collapse on just the access trail side. A failure at that location will reroute the majority of the water to that side, causing additional erosion to the access trail and opposite bank. A collapse of the access trail or driveway is possible in this scenario. The picture on this slide shows how much additional water is routed to the left side now. Also, we can see that even without a collapse, the access trail and opposite bank, both marked with red boxes, are showing signs of erosion. The do nothing alternative is more expensive in terms of both money and damage to the site than any of the next three alternatives discussed. Alternative 1, due to the limited access to the dam, requires a mid-sized excavator to break up the dam into smaller pieces, then load the pieces into a telehandler, which can sit at the top of the access trail and load a triaxle to haul out the material. We looked at options such as a skid steer or mini all-terrain dump truck. Both would have to make multiple trips up and down the access trail, which has multiple tree trunks and large boulders protruding from the ground. Additionally, using the mini dump would mean an additional machine would then have to load the material into the triaxle. Alternative 2 still uses a small excavator to remove the dam. However, in this alternative, we would repair the access driveway and trail beforehand. The trail would require an extra day with the excavator to remove tree stumps and boulders. Then the trail and driveway could be graded with a Harley rake attachment on a skid steer. Finally, a woven felt and a base layer of riprap would be applied, and then at this point, the excavator will enter the creek bed and begin removing the dam. Pieces of the dam will be loaded into the skid steer, which will deposit them in a rock pulverizer located at the top of the access trail. The pulverized dam pieces can be used as additional base layer. Once the excavator and rock pulverizer are done, they should be removed from the site. 2B gravel can be trucked in and graded with the skid steer before the site is returned to the landowner. Like alternative 2, alternative 3 involves repairing the access to the site. However, instead of pulverizing the rock and using it as a base layer, the rock will be dumped at the top of the access trail in a laydown area. At a later date, the equipment will be returned to the site to distribute the rock upstream along the creek bed. Plans will have to be made to return at a date when the creek bed is dry enough to move equipment. Also, additional riprap will need to be purchased to account for the material from the dam that is not being used. The access trail and the road will also need regraded after the equipment is moved out the second time.
And from the three alternatives, the team and I had gone ahead and created an alternative estimates tab sheet. It is important to note that these are strictly considering the cost of labor, equipment, and materials. This also does not include the cost of engineering or risk analysis. Also important to note that the do nothing alternative was not included in this because of the risk of safety and the high cost price point. So from there, us as a team and Lisa had gotten together and we had determined that alternative 2 was the most feasible option for our project. This is because it improves the private and public access, improves the site safety. It has minimal site disturbance as compared to alternative 3, and it is more environmentally friendly than alternative 1. One of the main aspects of alternative 2 is the addressing of the access to the driveway and trail. From there, we will look at the large ruts, potholes, tree stumps, and anything that will need to be managed before the beginning of the deconstruction of the dam. Alternative 2 does this by repairing the road / trail and reuses the dam materials on site to ensure the complete repair of the road. So this would be the site disturbance area of alternative 2. Alternative 2 results in less site disturbance than 3. The laydown area off the access road can be eliminated at the end of the project with minimal disturbance, and there will be no disturbance of the soil or banks upstream from the dam, and the dam material is in no risk of machinery getting stuck or not being able to be removed from the creek bed. So from this, this job is obviously still dangerous. So the team and I had gone ahead and devised a site safety plan and hospitalization route. The site safety plan was created to be implemented on the job site in order to ensure that all the contractors present on the job site understand the potential risk and dangers associated with the project. A one-call list and the closest hospital route has been mapped out as a part of the site safety plan. This is to ensure that if there does happen to be an issue on the project, that anybody that is on site can manage to get to the hospital with the safest and fastest route. I'm now going to pass it off to Andre to finish up with the ENS and scheduling.
All right, here we go. So for our erosion and sediment plan, we first looked at the current subsurface as well as the existing site conditions to help us figure out how to best proceed. We decided that during removal, we are going to be regrading the access road, the access path, and connecting the gap between the access path and the flat bedrock area, as you can see on the image on the right. This will allow for easier access for our machines as well as our laborers. Post removal, we will not be adding any vegetation because of the heavy bedrock presence, which already limits their growth. The steel removed from the dam will be disposed of off-site, while the concrete removed from the dam will be crushed up and used on the access road. From there, the creek and its surroundings will be monitored over the coming months. For the risk assessment, we first decided what some of the most likely things that could go wrong in this specific project would be, and then determined the probability of each of those events occurring and the impact it would have on our overall project, each on a scale of 1 to 5. From there, we were able to determine the probability of it occurring as a percentage. So by multiplying the estimated cost of the event and the probability percentage, we were able to put a monetary value on the contingency that would later be applied to our overall cost estimate. The color scale of the contingency amount increases, with white being the least costly, and the redder it gets, the more it costs us if it were to occur. Although we already knew that alternative 2 would be the most viable option, as well as the safest, we still ran the same assessment for each option, and doing so confirmed that this alternative offered the least risk. So next, we'll take a look at our schedule. The main focus of phase 1 is to clean up the access road and the path, and then to regrade it. To do this, we plan on taking a Harley rake to first loosen the base, as well as an excavator to get rid of any stumps or large rocks that may be in the way. From there, we will grade the road and the trail and then overlay woven felt and a base layer of riprap. Phase 2 is the removal of the dam itself, as well as the disposal of the material. To do this, we're going to remove the dam in small sections in order to allow the water to drain slowly. We then will crush up the removed concrete and rock and add it over the riprap layer as a supplement to the 2B gravel we use in phase 3. The steel components of the dam are then removed and disposed of off-site. So the third and final phase is adding 2B gravel to the access road to provide a smooth new road that can be used by the public safely if necessary. Finally, we have to demobilize the equipment and haul out anything else that may be left on site. So from here, we were then able to generate a total cost estimate of the project that included material, engineering costs, mobilization, demobilization, profit, risk, labor, and equipment that would be required for this project. As you can see, the majority of the cost estimate is made up of labor, equipment, and material, which totals out to $21,800. The rest of our cost brings the overall Jacobs Creek dam removal to roughly $29,000. So from here, I'll pass on to Mike to kind of recap our project.
We wanted to end with a few slides showing what the site will look like over 3 periods of time. This photo shows the area before removal of the dam, while this slide shows what the area will look like immediately after construction. You can see that the water around the island will recede, making it appear as though it's larger. However, as time goes on, the water will push that debris downstream and the island will shrink. So to recap, we showed the site and discussed the safety concerns. We explained the hydraulic and hydrologic modeling, as well as what testing and sampling was done at the site. We completed the permitting packet, presented removal options, and gave our recommendation, alternative number 2. We explained our reasoning behind that determination and presented what the site will look like post-construction. We would also like to take a minute to acknowledge all of the individuals that helped us along the way. And finally, we would like to thank everybody that took the time to watch our presentation.